So this is an old question, but I notice sometimes CIE, they like to take old question and then they modify a bit, then they make it into a new question, but they're testing the same ideas. So if you understand the ideas, it should be okay, trust yourself. So if let's say you have a sphere and the sphere is rotating, and imagine this is you are standing on the sphere, of course not drawn to scale, because if you are this big, I don't know what you are, Godzilla, but you are also rotating, right? You're rotating around together with the Earth, okay? So this is the small object of mass m, this is you, mass m, at rest on the equator of the planet. Surface of the planet exerts a normal reaction force on the mass. Okay, so in order to not make that diagram looking too complicated, I will draw the forces. There will be normal force here, N. So think about the normal force. It has to be 90 degrees to the Earth's surface. So if this is the Earth's surface, then this is the normal force. Okay, and then state the formula of mm, r, and omega. Gravitational force, this is all question now where they write, you get marks for equation, gmm over r squared, okay? Make sure whatever symbol that you use that is not inside the question, so they already defined m and r, you probably need to define g, okay? So just mention g is gravitational constant. Next, the centripetal force required, Fc. So centripetal force required in terms of omega is mr omega squared, but lowercase m, no? Small m. Because the small object is the one moving in the circle. All right. So next, the normal reaction force exerted by the planet on the mass. Okay, so I draw again because I don't want to scroll here, scroll there. Your mass is here, right? So I know you are used to seeing yourself in a, okay, if I draw the human like that, it looks a bit weird lah. But you imagine this is you lah. Teacher, this is me, yeah, it's you. We are on the Earth's surface. The Earth is a sphere. We don't subscribe to flat Earth, okay? So in this case, your normal force will be in this direction, okay? 90 degrees to the surface of the ground. And then you will have your gravitational force in this direction. But your centripetal force is directed to the center of rotation, okay? Directed to the center of rotation like this, epsilon. This is a top view. Top view of this sphere. So again, for you, I'll just put this here. Because 3D sometimes a bit hard to brain now. Normally, when I teach this topic, I'll bring a basketball, or I'll borrow a basketball from the student sports complex and spin it around. But okay, so you imagine now I put my eye here. Okay, I look at the, I look at this thing, right? And then the human is here, no? Okay, top view. So the center, the circle is this plane. You imagine this part is your circle. And this circle is, from view from the top, it looks like horizontal. Okay. But in this case, right, when it's rotating, I can say the centripetal force is equal to net force. And then gravitational force minus normal force is equal to net force. Okay. Center facing positive, facing center away from center will get a negative sign. So if I want to find the normal reaction force N, it will be equal to the net force or the centripetal force plus the gravitational force. Is it right? Yes. No, wait. Negative. Sorry. Yeah. Negative net force. Okay, never mind. So this one will be gravitational force minus centripetal force. Okay. So just remember centripetal force is net force, number one. But also number two, net force is equal to gravitational force minus N. So in this case, don't leave your answer this way, you must put in the GMM inside. So this will be GMM over R squared minus MR omega squared. Explain why the normal reaction on the mass will have different values at the equator and at the pole. So this one is at equator. Okay, let's say I take very close to the pole, then I get this small circle, or this small tiny little circle. So at the pole, it's like your circle, your radius is very small. Okay, so if your radius is small, because now your n is equal to gmm over r square minus m r omega square. Okay, if your r is very small, this centripetal force is small. And then you might be saying, but teacher, this r square not small, man. No, when you are standing here, okay, I don't draw humor anymore, okay, I draw a dot. When you are standing here, because you're not at the equator, your mg is still in this direction, directed to the center of the earth. This is your gravitational force. But your centripetal force is in this direction. This is Fc. Does that make sense? Okay, so if you are at the equator, then it's very straightforward. The gravitational force is at the same plane of rotation. But if you're on top, gravitational force will pull you down towards the center of the earth. Okay, so in this case, this one becomes small because this r, this radius of circular motion is small. This r here is radius of Earth. Radius of Earth is more or less constant, so that one will not change. This 2r is only equal if we are at the equator. Only equal at equator. Make sense? Okay, so if you're at the equator, your normal force is different than at the pole. So I'll write all of that down. First point, I will say something along the lines where the centripetal force needed for circular motion at equator is greater due to a larger radius of circular motion. All right. I mean, this is the first point. And then you can say, since I write equation, N is equal to gravitational force minus centripetal force. You can then follow up and say the normal force at the equator is smaller than at the poles. Okay. So think about the fact that your weighing machine measures your normal force. So at the equator, you get a discount when you stand up and measure your weight after you eat too many ketupat or eat too much nasi lemak, and then you paranoid a bit, you go stand on your weighing scale. You're actually a bit lighter when you're, at the equator compared to if, let's say, you go to the North Pole or the South Poles, because part of your weight is used to provide centripetal force, and you need a larger amount of centripetal force because the circle has a large radius. Okay. Right, moving on to the next one. Let's see. The radius of the planet. Okay, so now they give you all the values. Radius of the planet is this much. It completes one revolution in this much. Okay. So we have R, we have omega, RE specifically. Calculate the magnitude of centripetal acceleration at the equator and at one of the poles. Okay, so this one is as straightforward as at equator. The R is equal to radius of the Earth. So you want to find the centripetal acceleration, you use R omega squared. So this one would be RE 2 pi over T squared. Okay, because F is mr omega square, what? But F is ma. So the m and m go away. So now we can put things inside. 6.4 times 10 to the power of 6. 2 pi over 8.6 times 10 to the power of 4. So very nice. They convert 24 hours to seconds for you. Good job. Okay, I'm going to press my calculator. It's faster if I press the manual one. It's 2 pi. Divide by 8.6. Don't forget your square though. Okay. So I got 0.0341. 0.034. Okay. Right, one of the poles. So you can say at the poles, you can assume that relatively speaking, the radius of circular motion is more or less equal to 0. So AC is equal to 0. Just write 0 here. My favorite number. Okay, next. Suggest 2 factors that could, in the case of a real planet, cause variation in the acceleration of free fall at the surface. Okay, so think about the acceleration of free fall. This is your G. Right, so we tell you many times, oh, G is 9.81, G is 9.81. But today, we're gonna talk about what this G actually means. Okay, but let's think about what we know already about this small G. We know normally we use G when we calculate things like weight. So weight, W is equal to mg, right? So then you're thinking, okay, so when I look at 9.81, it means 2 things. Number 1, it means meter per second square. This means, let's say I have a ball and now T equal to 0. Ball is stationary, V equals 0. And then after 1 second, when T is equal to 1, the V is 9.81. After 2 seconds, T equal to 2, the V is 9.81 times 2. Understand or not? This is acceleration. This is pecutan. So how much your velocity increase per unit time? 1 second at 9.81, 2 seconds at another 9.81, 3 seconds at another 9.81. So yeah, it's like a get rich scheme lah. Every person you manage to convince to buy Thermomix, you get commission times 3. I don't know what. Sorry, I got a lot of ads recently about Thermomix and I stress. And what's the other thing? The cloud one, Norwex. I think they market auntie things to me because I'm old or I'm the auntie age. But I don't have an auntie life, so I don't know why they market to wrong target. Anyway, sorry about that. So you times. So this is acceleration. That's why we call it gravitational acceleration. Another format is also G is equal to 9.81 Newton per kilogram. Meaning for every kg of particle that you have, because whenever you see kg, I want you to think about this one is related to the number of particles. All the little atoms and molecules that made out of you, that made you, contributes to your mass. That's why your mass is independent on many things. Like for example, the gravitational field. I don't care whether I put you on the moon, on Mars, on planet Earth, I dig a ravine and throw you inside, I put you in a black hole, your mass should stay the same unless I chop off your hair, then your mass will decrease, okay? So this means for every 1 kg of mass, it will experience 9.81 Newton. So let's say I buy 1 durian, and this durian is 1 kg. So if I let the durian, if I want to draw the forces on the durian, this is 9.81 Newton. I got a larger durian. Can you buy durian? They measure kg one, right? 2 kg. So then this one would be, the weight will be 9.81 times 2. They mean the same thing. So what could affect this force? Because this force is the one that causes the acceleration. You know, F is equal to MA. So if this is the only force acting on the object, I can say MA is equal to mg. So A is equal to G, which is 9.81. That's why they mean the same thing. I can replace my ball here with a durian. It doesn't matter whether it's a 1 kg durian or a 2 kg durian, it will fall in the same way. Okay, ignoring air resistance. So what will affect this G? Then now is the time to bring in. Number one, the planet is spinning. You know that, right? The planet is spinning. So if let's say this is the surface of the planet, and then this one I exaggerate. Okay, this is the surface of the planet is spinning this way. Okay, so if let's say before the durian reached the floor, the planet already spin a bit, the acceleration will change one. Okay, and also another thing about this acceleration is that it depends on the fact that the mass of the Earth is a perfect sphere. So a few problems are, because whenever you calculate this W, what equation do you use actually? You can use mg, but actually the gravitational force is G mm over r squared. Right? Durian is m. Okay. You measure from the center of the Earth. This is your r. So what is not constant? We made a lot of simplifying examples. The first thing that can choose to be not constant is r. You know, because we have Gunung Tahan and then we have Klang Valley. So the radius of the Earth is not uniform. Radius of Earth not uniform. Changes. It changes. That's all. It varies. Unless you boot up Minecraft Flatland, then can. But it changes. Okay. What else? You could say number two, they are nearby planetary objects like moon or planets. You could even say, teacher, you see, we think the mass is constant, but it's not. Maybe certain parts of the Earth is more water. More water means less mass compared to rock. So then there's less attraction. Okay, I'm going to add that in. Number three, density of Earth not uniform. There are many things you can use to suggest. Okay, but the changes is very small. So roughly speaking, it's still 9.81, as long as you're close to the Earth's surface. Okay, cool. That's it. That's the question. But I'm going to now segue into gravitational field. So if you got any questions regarding homework, you can ask after the break. Okay, they are related anyway. So you notice we've been using this equation for a while, right? This one is W equal to mg. We use so long already. And I already explained to you quantitatively. If let's say you want to explain to someone who doesn't know what 9.81 is, you can say, okay, everything that's 1 kg, 9.81 Newton force act on it. And this number actually tells us how strong the field is. Because if I go to the moon, and humanity has only been to the moon once, so let's say if I go to the moon, I know that the gravitational field is less. And then I take the same 1 kg durian and I drop it on the moon for science. Okay, this will not be 9.81 Newton. In fact, it will be 1.67 Newton. Because the gravitational field strength of moon is about 1/6, so around 1.67 Newton per kg. Around there, roughly. This one is 9.81. So from here, we can actually tell that the gravitational field is represented by this number. The bigger this number is, the stronger the field will be. You go to Jupiter, I think the field strength is about 14. And then suddenly you feel like very heavy. You want to lift up your leg, also very tired. You want to stand up, also very tired. Because when you stand up, you fight gravity. Your body is used to gravitational field. So you're okay. But if you go to the moon, oh, can you imagine how high you can jump? Let's say you go to the moon, you go up the moon, you can jump very high. You know why, right? Because gravity doesn't pull you down that much. So if maybe you go to the moon, you can join Olympics. But your Olympics from the moon, lah, and then you compare to us on gravity. Joking. Okay. All right. So to represent or to have a number to show how strong the field is, because where did we start our story about gravitational field or gravitational G field? We start our story by saying that field is a region of space where a body, like mass, experiences a gravitational force. But you know lah, in science, we always want to measure one. So now my question is, how strong is the gravitational field? How do I know? Strong, okay? So in physics, right, whenever we have something that is dependent on too many variables, because this force, you could say, teacher, very easy only. If the field is strong, the force is bigger, lor. Yes, if the field is strong, the force is bigger. But let's say the field, let's say I want to know how strong is M1. And then I look at the force on M2. And then your argument could be, but teacher, M2, the force also depends on M2. And because the force depends on both M1 and M2, called two factors, we want to isolate it out. Okay, we want to be able to say, okay, I don't want the number to be dependent on M2. I don't want. Just like I want 9.81 to be a number that is independent of whether it's a 1 kg durian or a 1000 kg elephant. Same, gravitational field strength is the same. So we want a standard number. So when you buy durian, let's say you go and buy Musang King, you don't want this durian 13 ringgit, that durian 130 ringgit, and you say, oh, I buy the cheaper one. You also know it's not that case, right? It's always how much per kg. So it's you pay how much money per kg. So instead of having the force stated as Newton, we go for Newton per kg. Okay, and this per kg thing, this will not be the first time you see it. All right, so let me put some lines and start writing. Okay, so say I go back to this part. Okay, and I want to steal this picture because I'm lazy to draw again. Okay, so let's say like this. And now we are going to try to find out how strong is the field. So this is defined as, because it's physics, gravitational field strength. Okay, so the question now for me is, I want to know at this point here, at the distance r from M1, how strong is the field of M1 here? Like specifically here, how strong is the field? Okay, then you go like, well, since this force is a consequence of the field, I'm going to put a mass here to test it, testing. So here, I will put a test mass. Can it be M2? Sure, M2 can be your test mass. But normally we take 1 unit mass. So normally in science, our testing one is normally a unit of 1. And then I measure this force. So later, if you're going to put a 50 kg thing here, you just take that value, multiply by 50. Okay? It's a bit like you want to buy cengkodok and then the auntie say, oh, 1 for 30 cents. She's not going to tell you, you want to buy 1 30 cents, 2 for 60 cents, 3 for 90 cents. The auntie don't have time to do the calculation for you. She will just tell you 1 30 cents, you do the math based on how much you want. So same thing here, 1 kg, this much mass. Okay, so we then will be able to define gravitational field strength G as force per unit mass. That's all. Not so much. This G can be defined as gravitational force over M, or F1 on 2. But this M is GMM over R squared. But you divide by M. Or you can say, but teacher, the M is 1 kg. Yeah, I know, but it doesn't matter because you divide them, then they cancel out. Just like here, it doesn't matter. The mass cancels out. Okay, so we frame gravitational field in such a way where it is easy to visualize and easy to use. Everyone will have the same amount of gravitational field strength, which is GM over R squared. That's all. So we have 4 pillars. Now 2 is completed. Okay, let's zoom out a bit. We have F is equal to GMM over R squared. Okay, and then if you want to find how strong the field is, got force, they only got field ma. You want to find how strong the field is, your G is force per unit mass. Second pillar is done. We now have a wall. And we can do some questions, okay? GM over R squared, because you divide by one of the M's. But I also need you to understand that there are a few properties about this gravitational field or how we represent them, all right? Number one, normally when we draw gravitational field, so the first thing you need to know is definition. Second thing you need to know is equation. Okay, like usually I will also tell students the unit is Newton per kg. We have discussed this before, or meter per second square. And this, my friend, is a vector. So vector, you don't assign positive, negative sign up to you. You look at your direction. Decide which direction you want to be positive. We will do some questions later. Okay. Number 3, can define, can write equation. What is next? Must be able to graph. Oh. So if you look at your A2 skill set, every single chapter is, most chapter will have define equation, if got equation, graph something. If there is an equation, you definitely can graph, and explain some stuff. So there are certain chapters where it's like medical physics, where there's less calculation and more explanation. But most physics will have all these key skill. One can define or not, can write equation or not, can draw graph or not. Okay, so we're going to graph the basic one here. So now I know already, if I want to be able to visualize the field strength of M1, I'm just going to call this G1, okay? From the surface onwards, because I can't put anything inside the planet, right? I'm going to get this infinity would touch 0 lah, okay? Because G is inversely proportional to R squared. So I get an inversely proportional. Teacher, inside leh? Inside how? Wait, that one, then wait first. Extension, extra. Not clear if in syllabus, so I teach extra. Okay, so graph, normally you graph 1, but maybe 1 mass or 1 planet or 1 star, maybe you need to graph 2 as well. We will draw that later. All right. Okay, other skills that you need to know besides definition, equation, graphing it, is also to be able to draw and describe the field lines. How whenever you study field, can see the field, unless you got magic eye, I also cannot see the field. And because we cannot see the field, we must be able to draw a picture or a diagram to help our brain. You know, our brain need picture. Okay, so when we talk about drawing and describing field lines, let's go down a bit. I am talking about the standard one. You have a little planet here, M1. Okay, and then you have these field lines that is normally radial. You can see. And it's always directed inside. Always think about field lines as GPS, not GPS, as the, you know, the arrow sign for the lost people. When you go to a new building, you see got arrow, tandas here. canteen there, library here. It's arrow for the lost mass. So these are all showing us the direction of gravitational force. This one should already start in AS. So this is G field. How will we describe this? Terms that we will use is number one, 90 degree to the surface. Okay, so 90 degree to surface. We also call this a radial field because it's along the radius. You see here to here, radius. Along the radius, here to here, along the radius, they are radial field. Okay, and this is always attractive. If you can find a repulsive gravitational field, please let me know. I want to go and break science, like Einstein broke science in 1920s and we never really recovered. But yeah, let me know. I would like to break science. If not, we're still sticking to 90 degrees. Okay, what do you have? You like this? Okay. All right. I think we are good on the theory side, but just let me see if I'm missing out anything with descriptive words. Nope. Okay, that's all. Describe the field. No need to draw. They normally ask you to describe. All right, we can move on now. We'll bring the keywords down. We'll do a question now. Okay, so to properly understand the types of question that they will require of you, let's try and start with something easy first. Start easy, warm up. And a recent question. Yes, recent. This is from winter 18. So if you print out the handout, this is page 33. Okay. Winter 18, paper 4-2, question 1. Bonus question. State what is meant by gravitational field strength. G. Gravitational force per unit mass. 10 years later, remember we were doing questions from 2008. This is 2018. Gravitational force per unit mass. Okay, 1 mark, move on. Explain why at the surface, the gravitational field strength is equal to the acceleration of free fall. So basically, YG is equal to 9.81 is equal to A of free fall. This kind of question and 1 mark. So don't overthink it. What do you know? Let's say you have an object. Okay, what is the force acting on it? Net force. Near the surface, the net force W is equal to mg. Centripetal force, all negligible. Okay, don't think about centripetal force unless the question asks you about centripetal force. Then only about centripetal force. If not, negligible, 0.034. It's nothing. Okay, it's not even 1%. So it's okay. It's okay to not talk about it. All right, so we're going to start off with this one. We can say that the gravitational force, G force, on the object F is equal to mg. But also from Newton's second law, F is equal to ma. So hence mg equal ma. We can also say this is also the net force. So G equal to A. All right. So 1 mark, actually not 1 mark, everything is 1 mark. If you relate these two canons, you explain properly. The force on the object is mg, and Newton's second law, you can write mg is ma. Bonus. Okay, next. An isolated uniform spherical planet has a radius r. Fine. I'm gonna put my planet here. Whoops. There you go. I'm gonna put my planet here. So my planet has a radius r, and on the surface is g. Sketch a graph to show how the acceleration of free fall, or basically g, changes with distance from the center of the planet for values in the range of r to 4r. Okay, time to draw a circle. This one is the center, okay? Because here the value is 0. You measure away from the center, okay? The surface is r. Radius is r. So this is my planet lah. Bit of a lopsided one. You get the point. This is my planet. All right. So we know at the surface is 1g. So this one. So I'm gonna make it a bit bigger. Okay. So the surface is g, and I'm gonna plot here. This is r. What happens at 2r? Zoom out a bit. G is inversely proportional to r squared. Okay, so if you are if you generally don't really do proportional very well, it's okay. We are starting with r, 2r, 3r. But because it's 1 over, like the further you go, the weaker it is. So this one will be g. Oh, crash. Why you crash? Gravitation too exciting. Are we okay? Hello. One note, you're fine. Good. Please stay same. Hang on, let me name this first. Normally when I don't name, also weird things happen. Okay, good now. I'll rename it later. Where are we? Wow, oh my 2r, oh, where did you go? Okay, 2r and r. This is g. Okay, so at r, this is g, but because it's 1 over r squared, if you double the distance, this will be g over 4, because it's g over 2 squared. So g over 4 would be here. Okay, and then for 3r, this will be g over 9, which is g over 3 squared. Okay, if you need me to explain a bit in depth about directly proportional, again, let me know, because my student needed it. If you don't need it, I'm just going to assume you don't need it. Don't be shy. It's okay. Just ask. Or DM me at the site. I can explain during the break. So it's 0.11 anyway. 1 over 9. Why is 0.11? Hi, so hard to draw. So hard to draw. Anyway, I want to draw 4r first. 4r is g over 16 or g over 4 squared. Okay. So r 2 squared. 2r, so 2 squared. 3r, 3 squared. 4r, 4 squared. G over 16 is 0.625. So 0.625 is 0.25. 2.5 box. 0.625. 10. 0.0625. So 2.5 box here. Okay lah. And then if you want to 0.11 divided by, this will be 4.5 boxes. 1, 2, 3, 4, 5. Okay. All right. Let me teach you how to press calculator so that you don't have to rack your brain with weird scales. Okay. So here's how I use my calculator to help me plot the graph. I look at these 0.25, 10 boxes. I don't care. Okay. So if I divide by 10, it is 0.025. One small box is 0.025. 0.11, how many boxes? Then I just take 0.11. 4.4 boxes, I plot 4.5. Paper 4 can plot half box. Paper 5 never plot half box. Okay, so this would be 0.11, and the other one is what? 0.0625. This one is 2.5 boxes. Okay, so you use this to help you. How much is one box, and then treat it accordingly. Okay, we got 4 points. We can join like the constellation. Okay, in the smooth curve, join the plots. You have to pass through the important points, which is the ones that I have plotted, to get the total of 3 marks. This graph is 3 marks. Nice. I like these 3 marks. You don't really have to work that hard. Okay, so here are your criterions. Okay, the first one, you have a smooth curve. Okay, we normally agak-agak lah. It looks smooth to me, then can already. All right, and then must pass through this point, and this point, and this point. The 3 one they don't include lah. But you don't know which one they didn't include, so might as well you plot all the important points. Does that make sense? Okay. That's it for this question. Oh no, got part C. All right, so we define some stuff, we draw a graph, and now some numbers. Planet has a radius of this much, density of this much. Calculate the acceleration of free fall. All right, so a side note. For density, I write this way. And here is why I write this way, in case you are confused, because sometimes when you look at book, density is this symbol. Pronounced as rho. Let me make it bigger. Pronounced as rho. Do you see the problem if I actually write the exact symbol? You see the problem. It looks like P, my dear. If my density look like pressure, it may, and power, it may just conveniently go away, because when I write this, I'll write that, which looks a lot like P in my brain. Okay, so I want to differentiate density, I write like this. Maybe your teacher, to differentiate density, they will write this way. I don't know. But if you write this way, it still looks like P to me. But as long as you can differentiate, can already, okay? Because I check substitution. As a teacher, I look at substitution. So just a footnote on how you write rho. And if I write that, after a while, it will become E. Okay, now you know why. Okay, so I write that. You don't confuse. You write whatever you want. You know the difference. All right, we want to find the acceleration of free fall G R above. Oh, this one. Whenever I see above surface, I must highlight underscore bold. You know why? Because R is equal to 2R. Teacher, why? Well, this is your planet, right? Radius is R. And then we want this extra R from above the surface. So we are asking us, what is the G here? Sneaky, this question, very sneaky. Never mind. GM over 2R squared. I got you. All right, so it's 2R. Then you may be thinking to yourself, well, teacher, that was nice, and I'm stuck now because I got radius, but I ain't got no mass. But you got density. And the last time I checked, everything is a sphere. In fact, they just mentioned it's a uniform sphere. So you will have to find the mass of the object. So I KIV this one first, I park one side. So let's say this is me doing the exam, and now I do density. Density is mass over volume. Volume of the sphere is 4 over 3 pi r cubed. I just need to substitute my m. So I'm going to rearrange, okay? I have m is equal to density, hang on. 4 over 3 pi density r cubed. Can I put inside, right? Can I put inside? Yes, I can. So I'm going to slot it in. Okay. This will now be equal to G 4 over 3 pi rho r cubed divided by 4r squared. I'm very excited because I can cancel a lot of things. I can cancel the 4, bye-bye. I can cancel the r and r squared and r cubed, bye-bye. So what I have left is G is equal to, G pi rho r. Can substitute already. 6.67 times 10 to the power of -11. I better use different color. And pi will stay there as pi. We have density 4.0 times 10 to the power of 3. We have radius. Please, you see the km here. 3.4 times 10 to the power of 3 times 10 to the power of 3. Ooh. Sorry. Of course, you can find the mass and then only press. And then you substitute your mass and then you do your thing. But I think you know me by now. If I can write less, I'm always an advocate of write less lah. So I rather substitute, cancel, and simplify what I can before I put in the values. That is normally an easier path forward, so to speak.
Okay.
Yes.
Is there still the divided by 3 or no? In the
very good. You're following along. Where should I put the 3?
In the denominator.
So pi over 3 lah, or somewhere there lah.
Oh yeah, okay.
Okay. That's it for the question. I'll press calculator. Let me arrange this big cramped. So when substituting, you always got 2 choices. One, if you're the type where you want to slowly find your way, you write the equation, you notice you don't have mass, and then you go like, oh, let's find the mass first. So you find the mass at the side, and then you put back the value of m inside here. Okay, no problem. I like to substitute because sometimes they can ask me to prove this. Right? If I said question, I would also like prove this. So I should also know the technique lah. I got preference, but no book techniques. Okay, so if I press my calculator, hopefully what you get is 0.95 meter per second. So if you don't divide by 3, unfortunately, ladies and gentlemen, this one you cannot, you don't know lah, basically. You wouldn't know whether you mess up or not. Okay, so while cancelling, don't get too happy and leave out anybody. 3.4 times 6. Okay, 9599338. Okay, not 95. 9499. All right. I'm going to draw a box around this because this one, this is a good point here. This does not just apply to, or rather, maybe I derive from scratch, but the same steps. Okay, you copy first. Let me do some organizing, adjusting. Okay, I need a big blank space. On and close things that go. Wow, hang. Close things that I don't need. Like the 462 tabs that I've opened. Okay, hopefully you are somewhat done. I'm gonna steal some blank space first. Hang on. Inception its way here. Put this here. Good enough. Okay, extra. Which normally my students are like, teacher, where got place to write? I'm like, you want to pay more for photostat? Write down on your own notes or stick a post-it note. Okay, extra. 1. What about inside the Earth? Inside planet. Because we know outside the planet, it follows that 1 over r squared curve. Inside the planet, well, teacher, inside the planet got gravitational field. God. If don't have, it's very scary, okay? Imagine this is your planet. Okay, or your whatever, your sphere, your object. And then maybe you stay in Klang Valley. But if you stay below a certain, height or a certain y-axis height, then for some reason you have no gravitational field and you float. So if you dig low enough, you can float. I don't think it's the case. I don't know what you've heard, but no. So of course there's gravitational field inside the Earth. But then how do I continue my graph? Okay, let me start from here first. I know from here to here. Actually, let me make it smaller. Okay, so I know outside there is no debate because the only variable is distance. Okay, let's say this is the radius of the Earth RE. The only variable is distance. And let's say I talk about Earth here. This is Earth. Okay, good old Earth. 9.81 at the surface and go down. Okay, travel away, weaker and weaker, weaker and weaker. No problem. The question is here. What is going on here? Well, you could say, well, teacher, can I just not, draw like that? It's also a bit scary, The deeper you dig, the greater your gravitational field. So you reach the center of the Earth, your gravitational field is infinite. Is your Earth a black hole? Okay, all right. And there's no for one reason. You may be thinking, I can use this equation, what? Gm over r squared. So when r decrease, wouldn't G be bigger? Well, yes, but when r decrease, mass also decrease. The amount of mass that is attracting you is less. Let's say I drill into the metal of the Earth and then I dig like that. So if let's say like this, okay, so not to scale, but if let's say it's like this, only this part of the Earth is attracting me. Less and less Earth is attracting me. So this one drop and this one drop. So what's the net effect? Because when R drop, G is supposed to increase. But when M drop, G is supposed to decrease. So increase or decrease there? Don't know. Need to see which one has a stronger impact on the value of G. And in order to do that, I need to substitute M. See what I did there? Same like this one. I need to substitute M. The M very kacau. M change, R change, I cannot brain. I just want one variable, one independent variable to decide one dependent variable. Okay, X and Y. I don't want X and T and Y and then my brain hang. So if I can, I want to substitute my M. And I can obviously substitute this using density is mass per volume. And since density is mass per volume, my mass will be density times volume. Let me change color for you. So density times 4 over 3 pi r cubed. Okay, I'm not going to forget my over 3 now. Joking. Okay, so we're going to substitute into this M. Okay, so now if I substitute this in, my G will be equal to G big bracket density 4 over 3 pi r cubed. I don't know if you notice anything, but we can still cancel the r because the divide by r squared. So this one is bye-bye. And then what you have left is G is equal to 4 over 3 pi G rho r. all these things on front, all these here, are they not constant? 4/3 is constant, pi is constant, g is the gravitational constant. Density of the Earth is assumed to be constant. So everything here, we are going to assume constant. Okay. Is it a simplifying assumption? Yes. But it tells us a pattern. So you may not get a perfect graph, but you will get a trend that looks like that. All right. So assuming this is constant, including, so, but sometimes they can ask you like, what are the things that could make this not constant? Remember, we talk about G, the density of the Earth is not uniform. Density of Earth is uniform. So all these things, I can write this equation now as G is equal to KR. This whole thing I put K. Okay. Teacher, this graph is a straight line passing through the origin. Correct? Because here to here, G is proportional to R. But the curve here, G is proportional to 1 over R squared. I don't know whether it's in your syllabus. It didn't specify, but I always teach that. If you've never seen it before, it's probably because they have never asked before. But they have never said exclude, so I include them. Okay. So what have we learned so far? G can be calculated using this equation. It's defined as gravitational force per unit mass. The force on every kilogram of mass. Oftentimes, the calculation on its own is quite easy because it's just substituting values. Sometimes we like to play with density, so don't panic. Density can be substituted in terms of R. And then you can put it in, and then you can do the cancelling or whatever you need. All right. Remember that it obeys the inverse square law, 1 over R squared. The rest is fine. Yep. All right, so let's move on to something before we take a short break. I need to open another window so that tak lah kacau you kat sini. I want to do the double planet one because the single planet one is easy. So the next one that we'll do is a slightly older one. It's from Winter 10, paper 4.1. Again, don't worry if you tak sempat salin yang mana-mana, can look at the notes lah. I will upload in the same place every week without fail. If I forget or you want it earlier, ping me. All right, so next one I'm going to do is I'm going to turn back time and look at a slightly old question because this is a good one. Define gravitational field strength. Again, I don't ignore this unless within the day we define too many times already. Okay, gravitational force per unit mass. This kind of memory thing, more repeat, more memory. Okay, force per unit mass. All right, an isolated star has a radius r. Mass of the star can be considered to be a point mass at the center of the star. Gravitational field strength at the surface of the star is Gs. Okay, at surface, Gs. Let's plot. Go here, 1 Gs. Sketch a graph to show how it changes from R to 4R. So the difference between this and this is that this one starts from 0, and then this one starts from R. So please read. I don't go memorize the graph shape. This one no need to memorize. Okay. So we know it's going to be G to 0.25 G over 4 to G over 9, 0.11 G to 4R, 0.625 G. Then this one is old question lah. Okay. So because it's old question, you don't get the graph grid, but you can roughly estimate, I guess. 2,5 is somewhere here. This is only 2 marks. 3 is somewhere here. 4 is here. So that's smooth curve. Smooth curve. They will look at the starting point and the ending point. And because they give you like that, then it's a rough estimate. So 1 mark for the shape, and 1 mark if it passes this point and this point. By eye, judged by eye. Okay, part C. The Earth and the Moon may be considered to be spheres that are isolated in space. Okay, so they are alone lah. It's just both of them, just the two of us. Okay, so the mass of the Earth and the Moon is given. Okay, and the radius of the Earth is RE. Sure. The separation between the center and the Moon, the Earth and the Moon, is 60 RE. Okay, okay. 60 times away. I'm going to do this one because I need the diagram. Okay. Next part. Yeah, so we got Earth, we got Moon, separation 60 RE. Are we given RE? Not yet. Maybe later have to calculate. I don't know. All right, explain why there's a point between the Earth and the Moon at which the field strength is 0. Okay, let's see. If the field strength is 0, this means that the force is 0, right? Right, that is what it means by having field strength 0. So in this case, there is a point here where the force is 0. Now, if the force is 0, what does this tell us? It tells us that the Moon and the Earth is fighting, but the Moon is less mass, so the Moon field is less strong. And because the Moon field is less strong, I'm going to assume that the point where the force cancel off is closer to the Moon, closer to the weaker field. So Earth, look at the, let's say this is a rock here lah. Look at the rock and say, come to me. Attractive force of the Earth. The Moon be like, no, 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 come to me. So they are acting both in opposite direction. And if their magnitude is the same, the force will cancel out. And when the force cancel out, the field will cancel out. Okay, but here is a note about answering technique or technique menjawab a bit. When it comes to answering questions like this, it is a bit safer to talk about what they ask you to talk about. In this case, it is gravitational field strength. So while you can talk about force, it is better to talk about field, because I can draw this arrow to represent Fe and Fm, or I can substitute this with GE, because force F is equal to, or rather G is equal to F over M. They are both vectors. It's a bit like I take force and divide by a constant K. The direction is still the same. Vector A and vector KA will be in the same direction. Vector A and 2A and 10A and 46A, all in the same direction. So I'm going to draw GE, because it's acting on the same mass. No? Then here, this is GM. Okay. Direction of field lines and direction of force would be the same. So from here, I can say that the fields, G field, first thing first, this is vector. So G field of both Earth and Moon is in opposite direction. And why do we care that they are in opposite direction? Why do we care whether they have direction at all? Because it says everything right. They are vectors. Since both fields, since G field is vector, it will make no sense if one is vector and one is not. So G field is a vector quantity. the resultant field can be 0 because you subtract when magnitude of fields are equal for both Moon and Earth. Okay, so the mark here would be gravitational force of both Earth and Moon is opposite direction. 1 mark. Okay, then the other mark is when you say, oh, this is vector quantity, so resultant field can be 0. This is good enough already. I just wanted to make it like super clear. Which helps me answer part 2. Determine the distance in terms of RE from the center of the Earth at which this field is 0. Yeah? The field is 0 when the magnitude of fields are equal. So this means for your rock, the gravitational attraction of the Earth will be the same as the gravitational attraction of the Moon. Teacher, not Fe equal Fm, equilibrium force. Okay. You here, you G, mass of the Earth, mass of an object, divided by R square, Re square. Here will be G, mass of Moon, mass of the object. This is R, mass from the Moon square. You can see this mm will disappear, so you can just write like that. So you can start from here, you can also start from here. I prefer to start from here, again, left to right. So this will be G, mass of the Earth. Teacher, where is Re? Radius of the Earth, distance from the Earth. Okay, so I'm going to now, because they want you to find the distance from the center. So center of the Earth, yeah, we want to find the distance. Distance from here all the way to here. Assign your favorite alphabet X, A, M, N, whatever you like. But do we know this? Here to here. This will be 60 minus X. So if I want to find the gravitational field strength here, this will be G ME over X squared. And the Moon, this one will be G mass of the Moon over 60 minus X squared. We take this mass and then it's this distance. We take this mass and then it's this distance. Okay, can I put down there? This will be G ME over X squared. G mass of the Moon over 60 minus X. Whole thing square. Okay, G and G, faster, take away. Okay. I got students who straight away very excited and want to open the square. Why? Why you do this to yourself? Do not do this to yourself. This is not maths. I'm not going to do polynomials. I do not want to find the roots. I just want to find values of X. Okay. So I want to find values of X in terms of RE. Hang on, this is not 60. This is 60 RE. That's all I need. In terms of RE. Not real roots. I don't care. Just don't tell your maths teacher. Basically, it's not the point here. Okay, so let me move some stuff into this place. But I think we can substitute already. Okay, so don't do that. Bring all the squares together so you can square root. Okay, so I'm going to take 60 RE from here. 60 RE minus X. Okay, I'll find I squared like that. Okay, divided by X squared. Because this is easier. Later you can square root. Okay, right. Anyway, mass of the Moon is 7.4 times 10 to the power 22. mass of the Earth 6 times 10 to the power 24. So if I press my calculator, I want to keep fractions first at this point because I'm not yet at my final answer. So if for fraction, that'll be great. But then I bring over and square root. Okay. So 60 RE minus X over X is equal to square root of 37 over 3000. At this point, I give up and press calculator already. 60 RE minus X will be equal to 0.11. Guess you want to put another one also can. X. Okay. I rearrange. What do we want again? X in terms of RE. Okay, so I will rearrange this. And then I will have 60 RE is equal to, bring over here, plus 1.111. Yeah, sure, you will get number 1. So you can get X in terms of RE. 60 divided by 1.111. 54 R. Okay. Yes, it's within your syllabus. Okay, so it's been a while. Get ready for two-body questions. Normally, the two-body question they reserve for electric field one. Gravitational field, they ask other things. Because electric field, copy-paste the framework. The 4 pillars that we will build in gravitational field, we will steal the framework for electric field. So normally, when it's 2 objects, they prefer to ask in electric field. Or that is the trend lah. But, you know, they can go against the trend one. All right, anyway, last part, time to sketch. So you see, we calculated, we explain, we define, now to sketch. You see, questions will normally include at least 3 of these skills. Okay, we are going to show how the gravitational field strength at the surface, between the surface of the Earth and the surface of the Moon change. Okay, now I'm going to draw this, just so you know. On the surface of the Earth, we are talking about 9.81. Or rather, I can put G lah, GS. So this one is going to go like that. Right? Teacher, on the surface of the Moon, on the surface of the Moon is around GS over 6. How do I know it's over 6? I mean, if I put the values inside, I can tell you it's inside here. It's over 6. Okay, or basically less than Earth, less than. The scale doesn't matter. They didn't plot. They didn't give you a graph. And if they didn't give you any values, like for example, even if I put this on the graph grid, the accuracy does not really matter that much unless you calculated already, or unless they tell you to consider the magnitudes. You didn't find the magnitude of the Moon, cannot. So gravitational force of the Moon. Do you notice, or rather maybe I should just bring this over, that they are in opposite direction, GE and GM. Put down here so we can refer. Ta-da! In fact, I can even align this. Something like this-ish, more or less, judged by eye. So you notice GE and GM is this opposite direction. If it's opposite direction, somebody has to be negative. Okay. And who is that somebody, you ask? Well, since I already assigned GS as positive, I know we're going to be G Moon as negative. But this is not what they want you to draw. They want you to draw the resultant. The resultant G is GS plus GM, but GM is negative. So somewhere along the line here, they will cancel out. Okay, let me draw my GM a bit exaggerated a bit. So because this is something like that. So somewhere along the line here, I don't know, somewhere here lah, they will cancel out. You're adding the green graph to the purple graph. Okay, so the big green graph add a tiny purple graph, you get a slightly lesser gravitational field. So does the moon affect the objects on Earth? Yes. Tides. Air pasang, air surut. There, the water come, the water go away. Learn this in geography, right? Use the tides, okay? Got a bit lah. Does Earth's gravitational field affect the moon? Yeah, more significant because the moon's gravitational field is less. But we don't stay on the moon long enough to actually have any phenomena that you can observe. So if I add two graphs together, I'll get something like this. Okay, so close to the Earth gravitational field directed towards the Earth. I'm taking Earth-bound direction positive because I am an Earthling and I like Earth. Okay, you can flip the graph, or your graph can look like this. Also can. So it's this or this, as long as it's not symmetrical. Close to the Earth, Earth very strong. Then as you travel away from the Earth, it will be weaker, 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 weaker until this point here. This point 54 RE, where the Earth's gravitational field and the moon's gravitational field, they both cancel out. And when they both cancel out, what happens? The moon is like, my turn, my turn, hello, Earth, you chill a bit, bro. You already got 54. Chilled. So the remaining 6 RE, the moon's gravitational field will overtake or supersede the Earth's gravitational field because we are closer to the moon, and then it will attract towards the moon. Okay. If you're a maths person, I draw these two graphs and I say this blue graph here is the sum of both graphs, also can. G resultant. Teacher, this 3 marks, how to get? Old question. If new question they want to modify and they want you to really plot, they need to ask you to do a bit more calculation. But oh, what happened? Hello, excuse. Don't jump here, jump there. Okay. So G equal to 0, at least 2/3 distance, because we're talking about 54 RE. So 54 RE, sorry, screen. 54 RE is more than 2/3. So towards 2/3 is 40 RE. Okay. GE and GM in opposite direction. That means before the cutting point. You didn't draw this graph like that. So weird. Okay. Opposite direction and the correct curvature. So the correct curvature is decreasing gradient, minimum gradient, increasing gradient, not zero gradient. This is in maths. We call this inflection point, judged by I. And then this GE at the surface is bigger than GM. Make sense, lah? Okay. This is the inflection point. So the gradient decrease, you see here, decrease, 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 minimum, increase, increase, increase. But the gradient is always negative. Okay, so you could draw this shape, you could draw this shape, it doesn't matter because that one is direction of vector. All right. Okay, that's all for this one. Time to go for a 10-minute break before we continue. Take 10, go stretch. Or if you have anything you want to ask, you can ask in chat. I will set a time. I should pause recording, but there's no step. Oh my God.
Miss Lee, you're muted.
Okay, hi, I'm back. Anyway, as I was saying, if you haven't tried this question yet, I think it's assigned as last week's work. So please do it because next week I'm going to transition this question into paper 5. If you haven't done a theory, it's very hard to transition in paper 5. try lah, okay? 10 minutes of your time. Just want to mention that if you don't know that there are a few traps here, this is km power 3. So you have a kilo here, then got power 3, so it's 10 to the power of 3 power 3. So this is 10 to the power of 9. Okay, 10 to the power of 9. And then you see this day square. Okay, this one I let you convert. You have to convert to second square. Okay, always check the conversion before you calculate the gradient. Especially if you are required to find a physical constant. So go do the question. Okay, this one is because there's a more recent past year that I'll probably let you do a bit later. This one is ON 15 paper 4.3 question 1. This is page 10. All right. Okay, so we have a bit of time. So I'm going to start an introduction on the other two pillars because a wall does not make a house. Okay, so when you think about describing your field properties, okay, we talk about forces because forces is easy for us to experience or feel the effect of forces. But you see, accelerating or an object slow down, object is being pulled in that direction. Force is easy to visualize, easier than its counterpart. Okay, so always think about the triad between force, acceleration, and force and work done. Because remember how dynamics is always here to explain why, but this acceleration will lead you to your kinematics, your STUBA equation, your STUVA, okay? And work done here will lead to KE and PE. This is why, remember, when I started studying systems, force can help you explain why, but this tool is to help you explain what is going on. We can describe this in the perspective of work done or energy, can describe this from the perspective of velocity, acceleration, distance travel, time taken to travel that far. And because we are dealing with planet object, this part for gravitation is a little bit chacat lah. We don't use that much. Do we use circular orbit? A bit. Maybe for centripetal force, but not very common. We prefer this one. In fact, we like this so much because we can calculate energy at a greater accuracy when it is planet size. If I'm talking about sending a space probe to Mars, the time can be calculated, but it's very difficult. You know why? Because your acceleration is not constant. Energy is easier. This problem here is, you want to use this equation? Cannot. Teacher, why? Because A is not constant. Teacher, are you sure A is not constant? Dude, we just drew this graph. Have you seen this graph? Have you seen? It's not constant. If your acceleration will be looking like this, can you imagine if, let's say, you want to integrate to find velocity, integrate to find time? Wow, very headache. Okay, so you see the point now, all right? So that's why we prefer to defer to energy, because energy is scalar, and scalar is generally easier. So this one is a bit stuck. We are stuck because we don't have the maths, and we are stuck with because we don't know what's going on. So we prefer to focus on energy and work done. That's why the framework is like that. Okay, not that we don't want to do kinematics, we can, but maybe a bit later, because the force is not constant, the acceleration is not constant, we have a lot of headache. Okay, so right now, whenever there's force, we think about work done, especially when it comes to building the 4 pillars. Okay, so this force will do work. You know that, right? You take a force, apply on an object, do work. Okay, so when it comes to work done, the most basic one, the most vanilla format of work done is, I take a force and I pull a block. The block travels a distance S. Ding, 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 do, 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 S. To find work done, I find Fs. Yes, this one high school lah, okay? But after a while, you notice that we don't always apply force this way, correct? We apply force at an angle, we apply force as a random direction. That one we covered in your AS already. But so far, this F is constant. But what happens when the force is not constant? Because we know the force is not constant. We've been drawing all sorts of curves today, not constant, right? So if the force is not constant, have we encountered a scenario where the force is not constant? God, spring. Let's say you extend a spring from here, let's say x1, and you pull it, you pull the spring until it is a new extension x2. Do you think this is F? This is not going to be F anymore, you know, it's going to be a bigger F. If let's say x2 is 2x1, this is going to be 2F. Because you stretch the spring. The more you stretch, the more force you need. Still got proof. Got lah, my friend Hook. Have you heard of him? Captain Hook. Fx, it look like that. x1, x2. So this one will be F, and this one will be 2F. Okay. So if I want to find the work done to stretch the spring from x1 to x2, what do I look for again? Area under the Fx graph. So actually, although we told you that it's F against S, this one is hinged on the fact that they are both constant and you got condition one. Not only F have to be constant, F have also to be parallel to S. And if it's not parallel, we bring out our vector resolution resolve vector skills to make it parallel or take the parallel component. Okay. So if F is not parallel, you just ask yourself, well, can I use the equation? If F is not parallel, then we resolve. This one is mainly AS. Mainly AS, okay? Never see before already. Then this one, if it's not constant, if it's not parallel, we resolve. If it's not constant, we have to find area under the Fx graph. So for this one, you would take half Fx1 minus half 2Fx2. Sure, la modulus, whatever. Area under trapezium. Okay. Then you may be thinking, teacher, you see how we have a situation here. Our situation that our Fx graph is not a straight line, right? Is it a straight line? This is your Earth. Let me draw a nicer. This is our Mother Earth of any planet. I am big camera. Okay. And let's say I want to plot a graph outside lah. Okay, we only take outside of planet Earth. Just for easy conclusion. Okay, so right now I want to take an object. Let's say, don't take here, and then I want to move it around. Maybe I want to move it here. Maybe I want to move it, I don't know, here. Maybe I want to move it from here to here. I don't know. I just want to move an object around in the Earth's gravitational field. But you see, the Earth's, if I want to plot a graph of F against X, this is my graph. Start from 9.81 or whatever the post. Oh, shucks. Is there a problem here? So we have a few problems now. The only way to find the area under this curve is by integration, because there ain't no other way. to be able to any form of satisfactory estimate this area, right? So let's say work done now. Work done W. Excuse, can I change color? Work done. Please let me change color. By gravitational field is equal to area under fx graph. But now we need to be able to quantify what this work done is. All right. And when I say quantify, what I mean here is this W, or this one is work done by the gravitational. Because who are we studying? Who's our watak utama in this whole story? Gravitational field, teacher. We look at the force, we look at the field, we look at the force, we look at the field, all about gravitational field. So we are looking at the work done by the gravitational field. So consider the perspective of the gravitational field. The gravitational field here is attractive. It likes to pull things towards it. Okay. So in this case, it is work done by the gravitational field is area under fx graph. Second thing, second issue. I don't know where to start. Because previously, work done by gravitational field, this is actually defined as your gravitational potential energy. And when we say we don't know where to start, is we don't know where is GPE 0. Where is GPE 0? Teacher, do we need to know 0? I take the ball here. Let's say the ball is 2 meters above ground. I want to find GPE. I take mg times 2. Sure, but if I mean, this ground could be on the 2nd floor. And then below the ground, if I zoom in, the building here may be another 20 meters. And sure, the building may be on the hill. And the hill is another 100 meters. And sure, the hill, when measured inside, got river, got ocean, there is another 2 km. You get the point, right? Where is 0? I can continue. So if we take below at 0, we got problem. We also got so many problems. Don't know where is 0. This thing is not going to end anywhere. So then the scientists got stunned balik because this one tak boleh pakai, cannot use. And then we say, okay, if we teach student level 1 GPE, we just tell them take change in height. So we take 2 because probably you need to find, oh, what is the speed of the object here? So we take the change. This one is change. But right now, where is change? I tell you what, I know a point where the force is 0, and that point is infinity. Because if we go inside the earth, we go down, and we cannot find a 0 point, what do? We go in the opposite direction. Because I know the further I go, the weaker the force, and eventually when I reach my best point, infinity, the force is 0. So now I'm going to take my object, my whatever lah, meteor, rock, satellite, durian. I want to bring it towards the earth. So the earth is like, I'm very happy to attract the mass from infinity towards me. Okay. So let's say I attract the mass from infinity to the surface of the earth. Okay, I got running out of space, but let me move this a bit. So I'm going to bring the mass from here, okay, all the way to the surface of the earth. don't throw slipper at me. I try to be mindful that you may be copying the exact same thing that I'm drawing. So I don't want to move things too much around, but I cannot change color. Hello, excuse. Okay, never mind. We let this spinny thing spin first. Okay, so I'm going to bring something from infinity to a point inside the gravitational field. Okay, so by the point this one reach here, I'm going to assume that the distance here is r. Okay, the distance r in the gravitational field. Yeah, sorry, I have to change color this one. Pen don't cooperate. Okay, a few problems, not problems, a few situations to note. This force will be very strong, right? The force here, see the force here at infinity, the force is 0. So if you push it a bit, then maybe you got tiny force, tiny force. From infinity to, let's say, a point r in the gravitation. Of course, this r doesn't have to be on the surface. R can be here, R can be here, anywhere, anywhere. Between the surface to infinity, okay? But in order to find that, that would be the area under the graph, okay? Area under. Hello. What is wrong with my window? Let me check my task manager. Something is not right. Draining. But those of you who are a bit ahead of time, we are going to find the area under the graph by integration. Maybe you can tell me what equation should I integrate? Well, one node is sucking 1.5 gig. Good job, one node. Why you do this? No, let me close the start line. Can I use my highlighter now? Okay, great. Nah, we're looking for this area. So we're gonna have to integrate a bit. Okay, so I'll write the definition for you. So that is the story about why we define it in such a pelik way lah. Gravitational potential energy in A2 GPE is defined as work done in bringing an object from infinity. Why do we choose infinity? Because there is 0. 0 is good. From infinity to a point in the gravitational field. Okay, boss. All right, so definition. Work done bringing an object from infinity to a point in the gravitational field. Very far away, bring it over, like Thor. Work done for Thor's hand to attract his hammer. All right, not too much, let's integrate. Equation for F. F is equal to G M1. Okay, let's not call this big M. And then let's say this is tiny m. Tiny m is attracted GMM over R squared. So to find GPE or to find area under this graph, I have to integrate this one. This means W is equal to GPE. Symbol that we use in your syllabus is U. Most of the time, U is used for GPE, or they can use EP. They're not very consistent one lah, as long as you read the question and understand context, okay? This will be equal to integration F dx or F dr. I use dr, okay? So that means this one is R. Okay, so I'm going to introduce some limit. We are going to bring it from infinity. Don't worry. Limit infinity is okay. To the point R, big R, inside the gravitational field. Okay. F is G, big M, small m over R squared. Okay, infinity to R. We have equation of this curve, this one. I'm going to put it in. Take a breath. I integrate you, don't worry, just watch. Step 1. Constant, kick outside. Who is constant? Well, G is constant, M is constant. The other M also constant, right? Sure. Yeah, they're all constant. Unless you explode the world into half. Okay, so I'm just going to kick out the constant. G, M, M. Then what is left inside? It's the good old familiar 1 over R squared dr. So basically, we are integrating 1 over R squared. Everything that's constant, we push outside. Okay, our limits were from infinity to R. Okay, can G, M, M. Ding, ding, ding. 1 over R squared. R negative 2, right? So you want to integrate this. The negative 2 becomes negative 2 plus 1. And then this one is R negative 1. Then be sure to multiply by negative 1 in front. Okay, so it's negative 1 over R. Okay, at the side for you, if you need it, if you long time never integrate, I don't know. I don't know what's your progress right now in maths. Because normally I make friends with the maths teacher and like, oh, today what you're teaching? Recently, when was the last time you teach integration? You teach last week, I don't do this. Okay, so we're going to substitute the limits. GMM, bracket, negative 1 over R minus, okay, the maths teachers will kill me, but I don't teach maths, so it should be fine. Substitute infinity. Limit of R is to infinity for 1 over R. 0. This one, ding, 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 0. So this one is 0, meaning this one is negative G MM over R. Oh, wow, teacher. All the equations look the same, but not the same. I stress there. That's why don't memorize, get to know them. Then you know that they're actually not the same. It's like I tell you, oh, all my friends' sisters, they all look the same. Then you're like, no lah, they look different. You just don't know them. Okay. So right now, when you have this thing, there are a few things that we need to discuss before I round it off. So this is just to show you the derivation. This negative got meaning one. The meaning of this negative is to show you that number 1, the gravitational field is always attractive. Joe, what means? You know how when we started this story about work done lah, this lah, that lah, it always feels a bit weird. It feels weird to you because you are used to things falling down. So you are not used to thinking about infinity. So it's weird. And we understand that. But we have to define it this way because the first problem, we don't know where 0 is, or it's hard to define where 0 is besides infinity. And you want to know the second problem? Sometimes we would like to be able to look at a GPE graph and tell whether the object is traveling faster or slower. Okay, and because gravitational field is always attractive, so work is done by the gravitational field in bringing an object from infinity. So you imagine you got one object very far away, and then you tell the gravity, hello, gravitational field of Earth, you gonna help me? Earth is like, I got you, because I'm always attractive. So just nudge it a little bit in my direction, and I will take over and attract this thing over. So if you think about it from the perspective of the object, right? The object will begin to accelerate and travel faster and faster, faster and faster, faster and faster. Does that make sense? The object is accelerated. So if work is done by the gravitational field, and this means from infinity, the gravitational potential energy decreases from 0. Hence, GPE, you already 0 at infinity. So the GPE is always negative. Our good old gravitational field will always do the work for you. If gravitational field is doing the work for you, it's negative. They lose energy. So another term that Cambridge like to use besides work done by the gravitational field is or work got out. Now, I'm not used to work got out because I come from the Malaysia syllabus line. We like to say work done on or work done by, but I don't know. Work got out. So if the field is doing the work, the field loses energy. So from the perspective of this, as I continue this graph, and I want to draw a graph of potential energy, EP, okay, against distance, is going to be a negative graph. Okay, at infinity, it's going to be 0. And this one is going to curve this way. But it's an R graph, so it doesn't curve that steep. EP is negative GMM over R. So I get this graph. Not as steep as the F graph. Maybe I should draw the F graph steeper, but you get the point. It's not be like this. But at infinity, still 0. At infinity, there's no energy because there's no force. Okay. So right now, it's more like to get you warmed up to the idea that, number one, when we want to think about energy right now, it's not as simple as looking at change in height, okay? Because right now, we are talking about something where the force changes. If we go back to our initial understanding of potential energy where you use mgh, you are very close to the Earth's surface. So if I am very, very close to the Earth's surface and my force is constant, then can. But this one, force is not constant, very far from the Earth's surface. So now, if let's say I want to find work done, I have to integrate. I have to use this equation. Do you need to memorize the equation? Well, it's either memorize or derive. So this kind of long deriving, it's rather you get to know enough, you can write this. None of it is given in your formula sheet. I'm sorry. Okay, none of it is given in your formula sheet. You can't seem to progress in maths. It's okay. Which part of maths? Talk to me. I want to help. But if you're like, you know what, I see maths, can I, the peak, I don't want to look at it. Can, memorize the equation. I tell you a shortcut lah. You know a shortcut, but this is not legit one. It's haram one. Don't use. Don't use when you have to write formal definition. Cannot. Just like I will never write this in maths. 1 over infinity, your maths teacher will have an aneurysm. Cannot substitute infinity into a function. Cannot. Must write limit. But if you're like, you know what, I just want a shortcut way to help my brain because my brain is like GGing. So then you, this one, you times R. What happens when you times distance? Force times distance. It looks like that, long. Because you multiply by R now. See? But got negative and I cannot magic out the negative this way, okay? So you have to know why there's a negative here because of the way we integrate from infinity to that point. Okay, so things that you need to know is, number one, force is not constant. So to find potential energy, we cannot use mgh. We have to use this unless close to Earth's surface. That's AS stuff. Okay, don't want to know derivation? It's okay. use the equation. Okay. To help you memorize the equation, if you already know Newton's law of gravitation, you just multiply by distance r. Okay, if you multiply by distance r, then it will look like gmm over r because the r square will cancel. But the negative sign is missing. So you need to remember there's a negative sign there to show what? Attractive force, gravitational field help you pull the object in. You don't have to do any work. The gravity will help you pull the object in. And because gravity helps you pull the object in, the energy actually decreases. So if we go back to the whole, I got an object, and then if I go from here to here, GPE decrease, it actually makes sense because maybe this is negative 200,000. Maybe this is negative 1,000 because at infinity, this is 0. So any object will still fall from high potential to low potential. GPE will still decrease. That's why it's negative. Because from here to here, you can see as the mass approach Earth, the potential energy decreases. I don't care whether the mass is me letting go of my mouse and falling 30 cm to my table or a meteor coming towards Earth. It's the same idea. GPE will decrease. So it helps us frame our understanding. This one will drop, GPE decrease, but it's a negative number. So take some time to brain the negative number from a negative number to a bigger negative number. Decrease this way. Okay. So yeah. Okay, so I think our house construction is somewhat okay. We now have a tripod. W is equal to integration FBR, which is your EP. Okay, and then here you will have EP, potential energy, is GMM over R with a big fat negative in front. Okay. So next week, we will complete our house construction and probably finish up the syllabus. But this week, I'm going to give you maybe a paper 5 question to do, but also to try out the gravitational field strength question. Then we can finish this one. Okay, I want to get the integration out of the way so that you got time to think about this and then you can ask me some stuff. So this one need to digest a bit. Okay, so the main idea is force not the same. We have to bring it from, we define it, it's by definition. I really try to explain why it makes sense to define that way. If not, then the para scientists define that way. Like pH 7 is neutral. It's arbitrary one. They chose to define, we have to study. Okay, so at infinity is 0. Okay, so bring it closer. It makes sense. It makes sense to me. If it doesn't make sense to you, then just, okay, no, infinity is 0. So we start here as reference point. Then we integrate to find energy. Once we have an expression for energy, the implication is this 3 point. Why is there a negative? The negative shows us field is attractive. So whenever we move towards R, when mass approaches Earth, so when R decrease, EP decrease. Because when people look at this equation, they be like, teacher, when this R is small, doesn't it mean that the number is bigger? Yes, but it's a bigger negative number, so it still decreases. Okay, that's it. Next time I see you, we will be talking about satellites again. But now we are going to move satellite from one orbit to another orbit. Of course, we want to be Russian spy and spy on the Americans. We want to fly our satellite around. We need to talk about energy. Okay. All right. So that's all. Please do work. If you watch me do very nice, you need to go and do. Okay. I'll see you. I'll stay back for a bit if you got any questions. But yeah, that's it for today. We also did gravitational field. I think field is okay. Most people can get field because you've been playing with 9.81 for a while. I'm going to stop recording.